I would like to introduce to you the other important concept of a circuit, which is input and output impedance. And when we talk about the input impedance, that means that we want to look into the circuit from this part. And the amplifier has an input impedance like this, which is called a Z load. And basically, for most circuit, if we know the internal structures, we can calculate its input impedance. But for the circuit that is unknown to us, then it is difficult to base on calculation. So we can use the following method to calculate the input impedance. And the input impedance, this result, for example, is unknown. And first, we remove the R test here if there's no R test. Then we know that the voltage appear here will be equal to, for example, the V1. If this is the V1 here, or T here. And then but we don't know, since we don't know the Z load, then we place a resistor here, which is R test here. And when we put the R test here, then we can measure the voltage here again. So we call this one V2. And we know V2 will be equal to what? Will be equal to the Z load divided by R test plus Z load. This is V1. Okay, then we have to solve for the Z load. Okay, so we have the V2 multiplied by the R test plus V2 multiplied by the Z load, which will be equal to V1 multiplied by the Z load. Okay, so we can move this one to the other side. Then we have Z load V1 multiplied by V1 minus V2 will be equal to V2 multiplied by the R test. And then, okay, we have Z load will be equal to R test V2 V1 as V2. So this is our answer. So you just measure your system twice and you know the input impedance of the circuit. This is the circuit. This is the input impedance we want to know. Okay? And let me erase that. Let me talk about the output impedance. Same thing that we can calculate the output impedance. Here, this is our amplifier, and after the signal pass through here, we have the output. This is our signal. But all signal has the output impedance we call Z source. And we can measure the signal here. We can measure the signal here. We can measure the load outside here. we can measure the load outside here. If we don't have the load, then we know that this is its original voltage. Then this will be going to be V5, V1, and V1 will appear here too. Okay, but if we have the resistor here, we have the load resistor here, this is our load here, then this one become V2. Okay, this become V2. So V2 will be equal to what? Will be equal to V1, but it's voltage divided, where this is our load here. And here will be the Z source plus R load. Okay, this is quite opposite to here, right? A little bit different. So we can calculate this one. We multiply this, move this one. We move this one to here. Then we have V2 multiplied by the Z source plus V2 multiplied by the R load, which will be equal to V1, okay, by the R load. Of course, R load is known, right? So we can move this one around here. We can move this one around. So the V2, the Z source, will be equal to R load V1 minus V2. Okay, so then we have Z source. Let me erase this. Will be equal to, we subtract this one here. So will be equal to R load, okay, which will be equal to V1 over V2 minus 1. Okay, this one will be our output impedance. Okay, so let's explain why input impedance or output impedance is important. Let me use my handwriting note. For example, we have a circuit, something like this. If we have a common emitter circuit here, something like this. It's RC, this is RE, and this is VCC, this is ground, this is our input. Here we have the resistor here. So suppose we don't have the resistor here, okay, we connect it together here, so this is V in here. Okay, of course, we usually have a capacitor here. So we'll know the gain. What is the gain? For a common emitter amplifier, we know the gain is approximately minus RC over RE, right? This is our formula here. However, if I connect this one to a load, for example, this load is a speaker, something like a speaker, and usually speaker is 4 ohm to 8 ohm. Then we will make the problem. this resistor, this speaker has impedance RL. Then the gain will become, the minus RC in parallel with RL over RE. So let me state something more extreme. For example, this one is 100, this one is 20. So the originally the gain will be approximately 100 divided by 20, which will be equal to 5. But when the 8 ohm load is applied, then the gain becomes minus 100 in parallel with 8 divided by 20. And let's see how much is this. 100 plus 8. This one is approximately 8. 7 something. So this is 8 over 20. So this one becomes only 0.4. So the gain becomes less than 1. Originally, we want to amplify things. Then here we have problem because we have a very low gain. This is not what we expect. So that's why the output impedance is important. So if output impedance is small, then G is affected less. This is important. Okay. So for this kind of circuit, for the common emitter circuit, it's definitely not suitable to drive a 8 ohm load. Okay. So if the load is higher, for example, if load is, 200 ohm, then things will be better. The gain will be minus 200 in parallel with 100 divided by 200. And we know the 200 in parallel will be this one. So with 230. So this is around 67 ohm. No, this one is 20 only. So the gain will be 67 to 20 will be around 3.3 minus 3.3. It's still not far from 5. It's minus 5 here. Still not far from 5, so it's still amplified. So be sure that we look into the output impedance of the circuit. Of course, we also need to be careful with the input impedance. For example, if we have, we have a circuit and we have the input impedance Z, okay, and all the source has the output impedance here. It's output impedance. So Ri here, and this is V, and this is some circuit. And actually, if Z is small, then the voltage applied here, V in here, will be small because Vi will be equal to Z over Ri plus Z. But if Z is small, Vi is small. And this is definitely not we want, okay? That's why we need to calculate the input impedance and the output impedance.